Welcome back. Okay, so now we've talked about having magnetic fields. We've talked about what magnetic fields do to charges. Let's talk about what magnetic fields do to charges when they all gang up together. So consider I have a wire and I have an electron flowing through that wire. And of course, in this picture, the electron is going downward with some drift velocity Vd. And it's going to have, that means the current is actually going up the wire, but I know that that means that the negatively charged electron is actually going downward. If I want to calculate the force on this particular electron, all I have to do is say force is equal to QV cross B, right? But if I have lots of electrons, then I have to worry about summing all of these forces together, one force for each electron. And so the sum of the force is going to be the number of electrons times the charge of each electron times the velocity of the electron, which in this case is going to be Vd, right? The drift velocity is sort of the average velocity of the electrons, and then cross that with B. And this represents the force on all of the electrons that are sort of flowing through some segment of wire, right? This N is really the number of electrons, and then Q is the charge of the electrons, and V is their velocity. Now, I know what the actual charge of the electron is, so I'm going to go ahead and throw that minus sign in. So I'm going to say minus NE, remember E is always positive, Vd cross B. Okay, so this is the total force on that segment of wire, right? This is the force on all of the electrons in that segment of wire. But I can be a little bit cleverer about this, because generally when we're talking about electrons moving, it's not so important the absolute number, it's sort of more important what the density is. So if I rewrite the N, which is the number of electrons, as a density, I can see that the density is going to be the number density times the volume, which is going to be the cross-sectional area of the wire times its length, L. Okay, so A times L is the volume of the wire, N is the number density, and so the total number of electrons is going to be the number density times the area times the length, which allows me just to finally rewrite this as minus little n, the density, A, L, E, V cross B. Like with so many things in electricity and magnetism, I've taken what was a beautiful little expression and now I've defined it in a bunch of new terms, but I've done so actually for a reason, okay? And there are a couple of things that I want to notice about this. First, I've decomposed the volume of the wire so that I can really talk about the length and the area separately. And that's something that's come up before in these lectures. And I also now have the velocity of the electrons in here, and so I have a direction of the movement of the average electron, and I have that minus sign that accounts for the negative charge. Well, I have to add a couple more definitions before I can go any further, because I really know that there's something special about the wire, there's something special about the way that we normally measure wires, and that is that movement of all of those electrons is really better reflected as a current. Right? So I have information about the current in here. Mainly I have direction of current, and then I have L, which is the length of the segment. It's convention to combine both the direction of the current and the length of the segment into a single vector that we call the vector capital L. Okay? And what the vector capital L is it's a combination of the information about the length of the segment, and of course when I write down this vector L, I'm assuming that this segment length is something that's straight, right? So this works for a straight wire, not a curved wire at this point. But I have a straight wire of length L and a current direction, which I'm calling R hat. And those two pieces of information, length plus direction, combine to make this L vector. Okay? It's a little bit awkward because they're really two conflicting, or not conflicting, but they're two complementary pieces of information that I've combined into a single vector. And I've done so only so that the final answer, well, I haven't done so, physics has done so that the final answer looks a little bit more compact. Okay, but armed with this definition, and of course the recognition that the drift velocity, right? Oh, I added a minus sign by mistake. That the drift velocity is in the opposite direction of R hat. By replacing the drift velocity with the magnitude of the drift velocity, times r hat also gets rid of that minus sign. Okay, so let me make a note of it over here. I said that the drift velocity is equal to minus the magnitude of the drift velocity times r hat, because of course the electrons are moving in the opposite direction as the current. Okay, so that's where the r hat now enters into this symbol. But now that I have this, I have an L and an r hat in the definition of this force, so I can pull them together into that L vector. And the last pesky thing that I'm left with is this number density times the cross-sectional area times the electric charge. Well, I can tease this apart a little bit, because of course N is electrons per volume times an area times the charge of an electron. If I combine these things, I can see that area divided by volume, well, that's just going to give me 1 over a length. And if I look up here, I have charge of electron times number of electrons. Well, that's total electric charge. And so I'm left with electric charge per length. And what, of course, is electric charge per length? Well, that's the current. And so I get, after I've done all of this algebraic manipulation, that the total force on the wire, which for now I can replace now this sum of the forces, because I'm talking about the total force on the current, right? I'm talking about the total force on all of the electrons. The total force then, which I'm just going to call F, is equal to I L cross B. And that's the expression that's known as the Lorentz force. So this says if I have a wire, a segment of wire, which has some amount of current I flowing through it, and has some length L, and it's in some magnetic field B, then I can calculate the force on all of the current in that wire to be IL cross B. I can take that. I can also say, well, if the force is IL cross B, then if I don't have a perfectly long segment of wire, I can also apply this to an infinitesimally straight piece of wire. And so instead of having L as a macroscopic vector, L is going to be a differential. I can also rewrite this as a little bit of the force, dF, is going to be given by the current times dL cross B. Where this dl is still in the direction of the current and the length of the segment, but the length is infinitesimally small, and that's why it's contributing to an infinitesimally small amount of the force. Okay, let's apply this to two examples just to ground ourselves in what's going on. So I have two different wires, both of which the current is flowing down the page. Each of these wires has some length L, but on the left wire I have a magnetic field coming out of the board or out of the screen or it's coming towards us, and on the other side I have a magnetic field that's heading away from us. So for the left one, I know that the force is going to be equal to I L cross B. Well, let's do the right hand rule, right? So L is pointing downward because L is in the direction of the current. B is coming towards us, and therefore I have to do it this way. Therefore the magnetic force is going to be to the left. Okay. In the other example, I have I pointing downward. I have B now pointing away from us, and my magnetic force is going to be pointing towards the right. And so I see that I still have these cross products to worry about, right? I still have a magnetic force that's perpendicular to both I and B, and of course it changes direction if I change the direction of either one of the two vectors that contribute to it. Okay. I wish there was some easy way to remember this, right? I wish I could say, well, if you have a this and a this, then you're always gonna. It just doesn't work that way, right? Every time I have a segment of wire with a current flowing through it, I have to do the right-hand rule to figure out the direction of the magnetic force. Okay, let's do another example. So I have an interesting thing set up here where I have two long conducting rails, and I probably have to connect these two rails to some sort of battery or something over here so that I can maintain a potential difference across them. I might also need a resistor in order to control the current, but I have something set up on the right hand side so that there's a current flowing down the rail across this crossbar, which is set so that it can slide along the rails and then back to my battery. So the two rails are fixed, so I'm not going to worry about the magnetic force on those. But this darker rail is free to slide along to the left or to the right at will. And so my question is, what's going to happen to that? What's going to happen to that rail? Well, it's going to have a magnetic force acting on it because there's a current on a segment in the presence of a magnetic field. Let me call the distance between them at this point, let me call it d. Okay. So now I can calculate what is the force on what is the magnetic force on this segment. Well, I'm going to calculate the cross product using way 1 from the supplemental video earlier this week, and I'm going to do the magnitude, and then I'm going to take care of the direction. And I'm going to do it that way because I can see that the current is flowing down, the magnetic field is into the page, and therefore they're perpendicular to each other. And the sine of the angle between them is going to be 1 because the angle between them is 90 degrees. And so the magnitude of the force is going to be the magnitude of I, which is I, times the magnitude of L, which is D, times the magnitude of B, which I can just call B, right? So I'll say that B has magnitude B. B. Anyway. So this is the magnitude of the force. Well, what's its direction? Okay, I have to do the right-hand rule. So L is in the direction of the current, pointing downward. B is away from us. Therefore, there's a magnetic force. There's a magnetic force to the right, which is probably why I put the rail on the left side of the page. So there's going to be a force now on the current through this wire, and that force is going to be to the right. Well, okay, what's going to happen to the force as the rail moves to the right? Well, the current's not going to change because it's still in the same circuit, and so the current's going to be the same. So the force is going to be constant. So if I do F equals ma, right, then I can tell that IdB is going to be equal to the mass of this segment, which I guess I'll just call m, times the acceleration. Well, a isn't 0, right? A is IdB over m. Therefore, the rod's going to be accelerating to the right, right? Because there's a force on the current, and that force doesn't change, and the rod moves to the right, and it accelerates to the right, which means the speed is getting faster, which means the magnetic field is doing work. What? Is it the magnetic force is always perpendicular to the there's a subtlety here, okay? And I did not break physics with my example. Yes, it is true that the bar is moving to the right. Yes, it is true that the bar is accelerating to the right. But I have to think very carefully about what the charges are doing before I jump to this conclusion that the magnetic field is doing work. In fact, what's happening is that the magnetic field is causing all of the electrons in this bar to move to one side of the bar, right? The magnetic field is causing them to go on these little circular trajectories that's building up the current on one side of the bar. When I do that, I've moved all of the negative charge to one side, therefore leaving the rest of the bar kind of positively charged. Therefore, they're attracted to each other. By moving the charges, which did no work, I've separated charges, causing the charges that are affixed to the bar to feel an electric field. and electric fields can do work. And so, no. The magnetic field did no work. But it almost seemed like it did. What the magnetic field did was the magnetic field induced an electric field by moving charges around, and the electric field did work. Okay? That's the second piece of this great puzzle that we have. That I've made it so something that always is perpendicular to velocity has been able to manipulate charges to create an electric field, therefore giving us another piece of information that says the electric and the magnetic fields are somehow closely related to each other. But the magnetic field did no work. Even if magnetic forces in this approximation seem to be doing work, seem to be accelerating objects, they are not doing any work. Magnetic fields do no work. Magnetic fields don't do work. Okay, your take-home messages are: the force on a current looks a lot like the force on a moving charge, right? F is equal to IL cross B instead of QV cross B. It's a structure that looks very much like what we had before, and it's one that sort of intuitively makes sense, especially when I do a sort of an argument to derive where it comes from. And that actual expression is that F is equal to IL cross B, where L is this interesting vector that we've created for mathematical simplicity that contains information about the length of the segment and the direction of the current. Right? L is the length, the magnitude of L is the length of the segment, the direction of L is the direction of the current. And there's a subtlety when I use the expression for the magnetic force on a wire, the magnetic force on a current, and that is that I have to remember that the magnetic field is not doing any work, even though it seems like it's doing work. Right? This is an effective description, and so this force is doing more things than I give it credit for, or that it looks like it's doing just from the first calculation. Magnetic fields do no work.